Hello, everyone, and welcome to today's reading group where we're joined by Hey, who will be talking about her latest paper, GRetriever, which allows to embed graph neural network knowledge graphs into LLMs to reduce hallucination. Feel free to join us in the next reading group session on live happening every Monday, or to subscribe on the YouTube video to see more of these.
Hello, everyone. Thank you so much for joining me today. My name is Xiaoxin, and I'm a third-year PhD student at the National University of Singapore. Today, I will be presenting our recent work, Chat with your GRetriever, Retrieval-Augmented Generation for Textual Graph Understanding and Question Answering. This is a joint work with my amazing collaborators, Yijun, Yifei, Nitesh, Thomas, Yan, and my advisors, Xavier and Brian. So let's get started. Okay. Here is the quick overview of what we will be covering today. First, I will give you some introduction and background to set the stage of our work. Then we will review the recent literature on graphs and large language models. After that, we will dive into the details of our work, GRetriever. And finally, we will look at some future directions for further research. So let's get started. In recent years, foundation models have changed the frontier of AI. Most task-specific or dataset-specific paradigms have been replaced by foundation models. For example, in natural language processing, we have models like ChatGPT and Llama 3, and in computer vision, there are models like Segment Anything and Clip. The definition of foundation model is that there are models trained on broad data that can be adapted to a wide range of downstream tasks. To be more specific, they have a unifying task formulation that can support pre-training at large scale. And secondly, foundation models have a good unified model backbone and can handle different tasks with little or even no changes to the model backbone. And thirdly, they have found to be able to empower diverse downstream tasks in a zero-shot or few-shot manner. But despite this great success of foundation model in CV and NLP, we haven't seen such a significant breakthrough in the graph domain, even though graphs are incredibly useful and ubiquitous in real-world systems, such as social network, knowledge graph, molecule structures, and so on. The current mainstream approach is still training a standard graph neural network for each type of the graph and each type of the specific task. This kind of approach have several drawbacks. For example, they are trained on graphs from a single source, which means that if the model is trained for knowledge graph, then it is difficult to transfer it to like molecule graphs. And they can only perform one or a few tasks. For example, for those trained for node classification, they may be not optimal for link prediction or graph classification. Given these limitations, we naturally aim to establish a new graph foundation model. We hope it can possess some of the advantages of foundation model, such as supporting graphs from different sources, such as from citation network, social network, molecule graph, web link, and so on. We also hope it can be applicable to various tasks, such as link prediction, classification, reasoning, recommendation, and so on. And we also hope it can be generalizable to new tasks in a zero-shot or few-shot manner. One approach to achieve this transition from standard GNN to a new graph foundation model is to consider whether we can leverage existing foundation model. For example, can we leverage the LM to support the design of graph foundation model instead of training a new graph foundation model from scratch? And here's
okay. Now continue.
Okay, and here's the reason why we want to use LMs for graph foundation models. The first reason is that LMs can help to mitigate the inconsistency between the input features by using text as a unifying medium. For example, social network, knowledge graph, molecule structure, despite their differences in structure and semantics, actually all of them can be translated into some text description. This will allow us to process them uniformly. And after all of them are translated into text, we can directly input them into the LLM so that we can benefit from the pre-trained LLM's capability, such as their general knowledge, reasoning, in-context learning, generative abilities, and so on. Okay, so now we have covered the introduction and background on foundation model, graph foundation model, and the motivation for developing graph foundation models. So let's move on to the next section. In this part, we will review the latest research advances in integrating graphs and large language models.
Okay, then
Okay.
maybe first, like integrating different or having one graph foundation model for all sorts of graphs.
Mhm.
Yeah, okay, that's sort of the goal now. But then you mentioned a bunch of types of graphs, like knowledge graphs and social networks, where I think this sort of makes sense, and they maybe capture some similar information, and the yeah, what you learn from one graph might be helpful for the other graph as well. But then you also have molecules in there, which seems like completely useless for tasks related to social networks or knowledge graphs, and the other way around as well. So, yeah, can you comment on that? Like why? Yeah.
Okay. I got your idea, and maybe yeah, you are right in a sense that maybe maybe what we have learned from the social graph, knowledge graph, will not benefit for molecule graph. Yes, that's true, but the good thing about large language model is that they have some prior knowledge. They have already know something about the molecule graph. Let's say you tell it is a oxygen. It is a specific kind of atom. It will already know some property of it. So we don't, yeah. So this is some good thing about LM. Of course, it cannot handle all kinds of graph. That's true. Yeah.
Yeah, I guess I'm like a little, that's the sort of thing I would have said. If you now want to unify all the stuff and just put it through a graph neural network to do all of the things, then why not just turn it into a string which doesn't have your graph structure that you actually wanted to leverage with a graph neural network, I assume. Yeah, so why not just turn it all into a string and throw it into a large language model? But I guess that's what we are doing, and then the
Yeah.
graph neural networks come in later somehow. Okay, let's go to this GNN large language model recap. But then if we do that right, of course, let's not recap like what graphs are or so and what large language models are. Let's just yeah. Yeah, we know what graphs are.
Yeah. So maybe later you can see if the integration can solve the kind of. Yeah. Okay. Okay. So let's move on to part 2, the review of recent literature. Actually, last June, I open sourced a GitHub repo called Awesome Graph LM, collecting papers on integrating graphs and large language model. It started with like about 20 papers and was just a simple repo, but up to now it have expanded to over 100 papers and gain increasing attention. So I believe that this growth can reflect that the active interest in this research area. For the rest of the presentation, I will mainly focus on the TAGs, the test attributed graph. It is a kind of graph where the nodes or each are associated with test attributes. For example, for a social network, each node represents a paper, maybe containing title, abstract as the test attribute, and each represent the citation relationship among them. And according to the recent survey paper, we can broadly classify the existing papers into 2 major categories, LMs as enhancers and LMs as predictors. So let's start with the first category, LMs as enhancers. The main idea is to utilizing LMs to enhance the quality of node embeddings. This method can be understood as using LMs for data augmentation or as a tool to enrich the graph data. There are many different types of LM with different levels of accessibility for the embeddings. For those pre-trained language models such as BERT sentence transformer, or for those open source LMs such as Llama 3 and Frenty 5, their embeddings are accessible. Therefore, for this type of LMs, we can use them as enhancers from the embedding space. Actually, previously, maybe surprisingly, some popular benchmark of TAGs still use shallow embedding for encoding the text attribute. For example, Cora used back-of-word features, PubMed used TF-IDF, OGBN archive used the skip-gram model, and this shallow embedding method have limited semantic expressivity. So you can think of, if we have the language model or large language model, we can significantly improve the quality of the node embedding. So specifically, we can fine-tune the language model on this text attribute. And then we can use the fine-tuned language model to generate some high-quality embeddings as input for the GNN. So together with the graph structure, we can train the GNN for some downstream task. And experimentally, we have see that the language model-based embeddings performs better than the shallow embedding-based pipeline. And there are another type of LMs, the closed source one. They are often the most powerful and high-performing models. Their embeddings are not accessible, so the embedding-based method we discussed earlier cannot be used. For this type of LLMs, we propose another approach, using LLMs as enhancers from the text space. A typical example is our work presented at iClear this year, entitled Tape. The main idea is to use explanations as features. So using the citation network as an example, the first step is to construct a prompt that asks the LM to classify the paper and explain its decision-making process. Specifically, after providing the paper's title abstract, we will ask the LM which archive CS category this paper belongs to, and ask it to give 5 likely answers and explain its decision. And the yellow boxes show how the LM respond and explain. So why using LMs as explanations? Using explanations as features is effective? To put it simply, you can think of the LM as a teacher, and the text we provide is like the textbook content, and the LM can process the content and then combine it with its prior knowledge and offer its answer and its decision-making process. So we believe this kind of explanation is easier to understand for smaller models like GNN. And in the second step, we will fine-tune the language model on these augmented features and then generate the features. And in the third step, we will train the GNN on these enriched features together with the graph structure on the downstream task. And these methods have achieved excellent results in many TAG tasks, including the large-scale OGBN archive. Specifically, as shown in the arrow on the right side, there is a leap in performance from using shallow embedding to using LMs as enhancers in the embedding space. And in this work, we further push the boundary by proposing the use of LMs as enhancers in the text space. And here's the link to the paper and the code. Okay, so let's maybe briefly summarize the takeaway message about using LMs as enhancers. The key idea is to use the LM to enhance the quality of the node embedding, either in the text space or in the embedding space. And and they have their both approach have their advantages and limitations. For the text-based method, they using their language model as a service compatible, which means that they are using the large language models as a black box. This will make them easier to integrate into the existing system. And these methods are particularly suitable for the tasks that require complex reasoning and for scenarios that need expert knowledge. However, they often require significant overhead when dealing with large-scale datasets. For example, if you are using ChatGPT, you may need to pay for the API costs, and if you are using some open source LM, you may need some GPU resources to do the training or do the inference. And for the embedding-based method, by using a simple cascading structure, such as combining the sentence transformer with any type of GNN, this method can be both effective and efficient. However, simply increasing the model size does not necessarily lead to substantial performance improvement, which means that if you replace the sentence transformer with like Llama 2 or Llama 3, then maybe there will not be much performance gain. So as you can see, both approach have their advantages and limitations. So the optimal choice really depends on your dataset and your task. Okay, so next, let's introduce LMs as predictor method. The main difference from LM as enhancers is that the primary executor of the task is no longer the GNN, but the LM itself. The main idea is to convert the graph into text or soft tokens that LM can comprehend. This is a work presented at ICLEA this year entitled Talk Like a Graph, and the approach is very straightforward. The idea is to translate the graph into text that LM can understand. Given a graph and a description of the graph task, we can design a graph encoder function to convert the graph into text. And then this text will be combined with concatenated with the question and then used as a prompt to query the LM, and the green box is the answer LM give to the graph task. And the main challenge of this kind of method is how to design the graph encoding function, because as you can see, there are many different types, many different ways you can describe a graph. So in this work, as shown in the figure below, they explore many different types of graph encoding function. And the conclusion is that graph encoding function have a significant impact on the LM reasoning capability. This is actually undesirable because it will require lots of human effort to design the optimal graph encoding function for each of the dataset. So given this limitation, subsequent work have explored representing graph as soft tokens. So the idea is to learn an encoding function that generates fine-tuned soft token instead of representing them just using pure text. For example, here, given a graph and a description of a graph task, we can design a graph token encoder to convert the graph into vectors, which can be either a GNN or graph transformer. Then these node embeddings or graph embeddings will be concatenated with the text tokens, and then will be fed into a frozen LM to generate the answer to the graph task. Okay, so let's summarize the advantages of and disadvantages of LMs as predictors methods. So this method, the idea is to represent a graph as text or as soft tokens that LM can comprehend, so that LM can make the decision and perform the graph task. And for graph as text, the benefit is that they can achieve good zero-shot performance. However, their performance will be significantly influenced by how we represent the graph as text. And maybe in this step, we will need a lot of human effort to design the optimal representation. Otherwise, it will limit the accuracy. And besides, it has a limited understanding of the graph structure, which can impact the accuracy of prediction for some complex graph-related tasks. Okay, and for the graph as tokens, for this kind of method, they can handle the graph inductive bias better than graph as text, because we have a GNN or graph transformer inside. They are designed for handling this kind of inductive bias. However, they require time-consuming prompt tuning to achieve the optimal performance, which can be a drawback. And it have limited few shot or zero shot capability because we have a GNN or graph transformer inside. And for now, we still need to chain a separate GNN for each type of dataset and for each type of task. So this will limit their zero shot or few shot generalization. So that concludes our discussion on LLM and GNN architecture. If you want to apply this method to your scenario, if you are focusing more on some traditional TAG tasks such as citation graph or recommendation, LLM as enhancers will be simpler and more efficient. But if you are more interested in some generative tasks such as question answering, or if you prioritize the explainability, then LLM as predictors will be more suitable. Okay. So after the previous introduction, I believe you will have some basic understanding of how to combine or how to integrate graph and large language models. So let's dive into the details of the Retrieval-Augmented generation for textual graph understanding and question answering. I will be covering the following aspect about why we want to what's the motivation and what's the challenge we encounter, and then we will talk about the details of the method. And in this work, we also propose a new GraphQA benchmark. And finally, we will conclude with the experiment and conclusion. Okay. So why we want to propose a new method? Because although there are some existing work integrating large language models and GNNs in various ways, they mostly focus on traditional graph tasks, such as node, edge, or graph classification, or on answering simple questions, or on simple or small graphs, such as the connectivity, finding the shortest path, and so on. And in contrast, in this work, we aim to develop a more flexible question answering framework that can handle more complex and real-world questions. For example, when given an explanation graph, which is similar to a mind map, we want to expand it into an essay. GRetriever can fulfill this kind of requirement. Even when faced with such complex and open-ended question, it can provide its answer based on its understanding of the graph. And to achieve this kind of framework, we need to tackle some challenge. The first issue is the lack of scalability. So previously, we have introduced how to translate a graph into some text description that LLM can comprehend. And for this kind of graph-to-text method, the limitation is that they will produce too many tokens if the input graph is huge. For example, if we have a graph with over 1,000 nodes, then if we represent each as a tuple, then we will have more than 5,000 tokens, which will exceed the context window size of most of the LLMs. The second issue is the hallucination. Large language models are prone to hallucination, which means that the generated content can be inaccurate or non-factual. And in this work, we identified that some graph LLM also have the as a bit the phenomenon of hallucination. For example, in a scene graph question answering task, the graph LLM maybe they will invent some non-existent edges or nodes, as highlighted in the red here. They will just generate some nodes or edges that is not exist in the graph. Okay, so to address these issues, we introduce the method of IG, Retrieval-Augmented Generation. IG was initially proposed to alleviate the hallucination problem in LLM. Consists of three main steps: retrieve the relevant knowledge from a large knowledge base, augment the question with the retrieved knowledge, and finally generate the responses based on the augmented input. So with the retrieved knowledge, LLMs can generate high quality and more trustworthy answers. And we want to generalize this benefit to the graph domain. GraphAG is designed to query the graph base and then retrieve the relevant subgraph, including the nodes and edges to augment the LLM's generation. So for example, here we have a knowledge graph, and given a question, we want to query the graph base and then to extract a relevant subgraph, a smaller subgraph, and then this subgraph will be used to assist the LM in generating an accurate response.
How do how does retrieval augmented generation for LLMs usually work? Like, how do we is this usually co-trained, this LLM and the retrieval mechanism? So is the LLM trained to expect something retrieved in its prompt or so? Yeah, can you maybe speak about that a little bit?
Okay, I'm asking the details of the how IG works for LM.
Yeah.
Okay, so for LM, first we need to build a knowledge base. It can be like a knowledge graph, or it can be some private or public database, or can even be a search engine. And then given a query, you will let's say the knowledge base is a database, and then you will calculate you will first encode your question into some vector representation, and then you will calculate the similarity between the query and the knowledge in your database. And then you will find the top K relevant knowledge. And then this top K retrieved knowledge will be used to augment your question.
Yeah, and is the okay, so and is the LLM then trained with the is the LLM trained in this setting, or do we just use a pre-trained LLM and not fine-tune it for this stuff at all?
Yeah, we can just use a pre-trained LLM. We don't need to train or tune it together with the retriever. Yeah.
Okay. And then is the LLM itself like used for this retrieval in any ways, for maybe aligning the retrieval outputs a little bit with
yeah. This is a more advanced type of method. So the most simple one is just use a retriever and then use the retrieve information and then use it as an input to a frozen LM. And we can also somehow to fine-tune the LM to align it with the retriever. So it is an advanced type of IG. Yeah.
And is the LLM ever used for doing the retrieval?
No. The retriever is a separate component. It is not part of the LM. Yeah.
So, okay. So you haven't seen any cases where people try to use the LLM for searching through your knowledge base while augmenting the input to the LLM and maybe doing something iterative or so.
You mean use LM to retrieve retrieve the knowledge?
Yes.
Yes, there are some work that cheating the LM's internal knowledge as the knowledge base.
Oh, okay. No, yeah, that's another one again, right? Okay, good. But then let's get to your graph retrieval stuff.
Okay. Okay. So we have talked about the challenges to design such a framework, and we can use GraphAG to mitigate this kind of challenge. And here is the details of the GRetriever. GRetriever integrates the strength of GNN, LM, and GraphAG, and it comprises of 4 main steps: indexing, retrieval, subgraph construction, and generation. So let's look at them step by step. So step 1 is indexing. First, we generate the node and each embedding using a pre-trained language model. And then we will store this node or each embeddings in, we will store them and then for later efficient retrieval. And then in the second step is retrieval. So when we have the question, we will encode the query using the same encoding the same encoding strategy, that is to use a frozen language model to encode it into some vector representation, and then we will retrieve the top k relevant nodes and edges from our storage. Let's say we have the question, what is the name of Justin Bieber's brother? Then we will retrieve the top 5 relevant nodes, like Justin Bieber, this is Justin Bieber, blah, blah, blah. And we will also retrieve the top 5 relevant each, such as sibling, hangout, friendship, and friend. Then in the next step, we will the first step is to construct a subgraph. So the goal here is to construct a subgraph that includes as many relevant nodes and edges as possible while keeping the overall size manageable. And here we formulate it as a PCST optimization problem. And here's the details. The PCST is an optimization method that allows us to find the most relevant connected subgraph. First, we will assign the price value to the nodes and edges, as shown in the green bubble here. If a node or an edge is more relevant to the query, it will receive a higher price value. In the previous step, we identified the top k nodes and edges, and here we will assign the price value to them in decreasing order from k to 1. For example, in previous step, we have known that the top 1 node is Justin Bieber, so this word will receive a price value of 5. And also for the top one edge, the sibling, it will receive a price value of 5. And then we will also define the cost of the edges, as shown in the yellow bubble. This will help us to control the overall size of the subgraph, because you can imagine that if we don't have any constraint on the edges, it will just expand the graph as large as possible so that we can cover as many prices as possible. And finally, we will run the PCST algorithm on the graph. The algorithm aims to find a subgraph that maximizes the total prices on the nodes and edges while minimizing the cost on the edges, thereby maximizing the overall benefit. Okay. And for the generation step, we use a model structure similar to most vision LLMs. So firstly, we will have a graph encoder to encode the retrieved subgraph. Then we introduce a projection layer to align the graph tokens with the vector space of the LLM. This alignment ensures that the LLM can effectively process the graph information and generate a coherent and accurate response. And then on the right side, we to leverage the text reasoning capability of the LLM, we also transform the retrieved subgraph into the text descriptions as shown in the gray box here. And then this textual subgraph will be encoded into text tokens. So finally, we will concatenate the graph tokens as shown in yellow and the text tokens as shown in blue, and we will concatenate them, and then this will be the input to the LLM. The loss will be backpropagated through the LLM self-attention layers to the graph encoder and the projection layer. The remaining parameters of the LLM will not be updated during this training process. So here is the overall architecture of GRetriever. Okay. And in addition to the method, we also propose a new GraphQA benchmark.
Sorry, can I ask a question, please? So
sure.
I'm a bit confused. Do you mean here that you optimize jointly the parameter space of the GNN that creates a graph token and the graph token itself?
I'm optimizing the graph encoder and the projection layer. And
yes,
yeah.
But then but the graph token itself is not optimized, meaning that you only shift the parameters of those two modules, but not the input graph, yes? And the input graph itself is just is it initialized by the retrieved LLM embeddings for the nodes and for the edges?
The input graph will not be optimized because the input graph, it will first be represented as the graph token, right? And then it will also be textualized into some text description. So
Yes.
yes. And we are only optimizing the projection and graph encoder part, and this will determine how the graph token are represented. So in some way, the graph token is changing during the process. Yeah.
I see. Yeah, and just last question. The embeddings stored in the index, they and the query itself, both of these embeddings are created by LLM that is not fine-tuned at all. So it is basically general purpose LLM.
Yeah,
and the query is a single vector. It's not a multi-vector query.
Do you mean that in step 1, the indexing, in this step, we are using another smaller language model to encode it into some representation? We are not using the large language model, right?
No, you're using the same large language model, right? My question was if the query was the textual query that is used to retrieve the original candidates for the subgraph creation, right? So this k nearest neighbor search. This is done based on a single vector. So you have single input vector, the query, and you are running KNN across the whole space of nodes and edges, and you retrieve those.
Yes.
Yeah. So I guess my concern is that in this setting, then you do not have a way to adjust for larger, more specific queries or smaller ones, right? So if your query implicitly contains like 10 entities or just 2 entities, there is no way to like you obviously can modulate it by choosing different K, for example, but it's not that flexible.
Do you mean that the input graph can be a small graph and a large graph, and I'm just selecting the top K node and edges?
Yeah. Yes.
Oh,
the query graph.
Oh, yeah. Actually, it is okay. Let's say the graph is extremely small. Let's say we are actually setting the K to a default value of 5, and if the number of nodes or number of edges is less than 5, then actually the whole graph will be selected as the retrieve graph. So
yeah, but okay, never mind. Thank you. Maybe I will ask something else later. Thank you.
Thank you. Okay, let me know if someone else have more questions.
Yeah, I have a small one. I just need a small clarification. After step 3, you end up with a subgraph, and when it goes to step number 4, there's a textualize operation there, right? So the textualize, is it same as the step 1?
Step 1. Okay.
Yeah. So you have a textualize. You textualize the subgraph, right? In step 4, and that textualize, is that same as what you do in step 1?
It is not the same. The textualize means that we are explicitly representing a graph as text. So we are trying to, like as shown in the gray box here, we are saying we are putting the node ID and then the node attribute here, and also how the nodes are connected to each other. So here's the source node ID, and then the relation and the destination node ID. So we are actually describing how the subgraph look like to the LM.
Oh, okay. Yeah, because it was just wasn't clear to me what that really means. Thanks. Yeah.
Yeah, textualize means we are describing the graph in text. Yeah. And in step 1, we are doing the opposite thing. We are trying to encode the text attribute into the vector representation, like for later retrieval. Yeah, and in step 4, we are actually translating it into text.
Thanks.
Okay. Okay, so maybe let's move on to the 4th part, the GraphAG benchmark. So here's the reason why we need a new benchmark, because the existing benchmark they mainly focus on pure graph-based reasoning task. For example, they may focus on some each existent or no degree, no count, each count, this kind of questions. But in our case, we want to focus on some real-world application involving textual graph. Such as the explanation graph, which require common sense reasoning, or scene graph question answering, which require visual question answering, and knowledge graph, which require also common sense reasoning. And our benchmark is designed to be more challenging and real-world set of graph understanding tasks. And for each of the data sample, it consists of a textual graph, a question related to the graph, and one or more corresponding answer. So here is how each of the data sample look like. And in the next part, I'm going to show some experimental results. So we show that GRetriever outperform large inference-only large language model, prompt tuning method, and LoRa-tuned LLMs. And the combination of our method with LoRa achieved the best performance, as we highlighted in bold. Okay, and we also show that GRetriever can improve the scalability. It significantly reduced the average number of tokens and nodes required to represent a graph, underscoring its potential in managing large-scale graph data. For example, on WebQSP, after applying retrieval, we can reduce the required number of tokens and nodes to just 1% and speed up the chaining. And we also show that GRetriever can mitigate hallucination. Here is a case study. We first instruct the model to answer graph-related question, specifically identifying the supporting node or edges from the graph. And then we will manually review the responses to verify the existence of the node or edges referenced in the model's output. For example, the word in red is some non-factual node or edges generated by LM, and the green one is the correct answer and existing node and edges. And we show that GRetriever significantly reduced hallucination by 54% compared to the baseline. And we also have done some ablation studies to show that there are performance drops when any of these components are removed. For example, if we remove the graph encoder or remove the projection layer, if we didn't textualize the graph, or we remove the GraphAG, there are some performance drop to different extent. Okay, so here we come to the conclusion. In this work, we propose a method that enables you to chat with your graph. It is a versatile GraphQA framework that can handle complex graph queries effectively. And specifically, we propose some advanced GraphAG techniques, which formulate the GraphAG as a PCST optimization problem, which can mitigate hallucination and enhance scalability. And we also propose a new benchmark for GraphQA. we have shown some empirical findings. We present that hallucination have also exist in graph LLMs, and we show the effectiveness and scalability of GRetriever, and we also provide a recipe about how to design the graph LLMs. And here are some takeaway message. If you want to design your own graph LLM, the first thing is representing graph as text is important, because it will allow LLMs to better utilize its reasoning abilities over text. Because after all, even though LLMs can like reason over other modality like graph or video or image, but after all, their reasoning abilities over text is the strongest one. So if possible, textualizing the graph is very useful. And the second message is that graph as tokens and graph as text can be complementary to each other, can enhancing the overall performance. So because in previous work, we have seen some work use graph as tokens and some work use graph as text. And actually they can be complementary, and you can try it out in your scenario. And finally, GraphAG is necessary for effectiveness and efficiency, because after applying IAG, we retrieve the most, we retrieve the relevant knowledge most relevant to the query. So this can help LLM to concentrate on the most important information, which is important for the effectiveness. And also it significantly reduce the number of nodes and number of edges, number of tokens required, which can greatly enhance the efficiency. So we think that GraphAG is very important. Okay, so for those who are interested in further details or reproducing our result, you can refer to our paper, repo, and blog post. Okay. In the final part, we'll discuss the future directions for our work. After large language models, we have seen some emerging multimodal large models. So there are type of large language models that can process and understand multiple types of data, including text, image, video, audio, like GPT-4. Here is how we here's the interface of the ChatGPT. Now we can upload the image or video, audio to the ChatGPT. It can understand it well, and we may wonder what about the graph modality? If we can incorporate the graph data seamlessly into LLM, so that maybe some researchers from other fields can easily leverage the graph learning method. And for now, for the multimodal learning, most of the existing work still focusing on some one-to-one mapping. So for example, for most multimodal model training, the training data they used is the image and text pair. They are just focusing on some one-to-one mapping relationship. But actually, in reality, the relationship between this multimodal data can be more diverse. We can actually graph can serve as a connector for this multimodal data. And if we consider this graph structure when maybe training or fine-tuning this multimodal models, maybe we can train better or more advanced multimodal models. So there are some potentials or opportunities to combine the multimodal learning and graph learning. Okay. So thank you all for your attention throughout this presentation. If you have further questions or would like to discuss any of this topic covered today, so feel free to let me know.
Thank you for a great presentation. I do have a couple more questions. The most important one, which I haven't understand that. So the GNN that you're training based on soft prompting, based on the gradient, propagated from decreasing perplexity of the LLM output. Is it retrained each time for each query, or is it trained on a bunch of queries during fine-tuning, and then it is frozen, and then we just reuse it?
Please wait a minute. Okay. Maybe let me briefly repeat your question. Do you mean that for the training we are freezing the large language model and just update the graph encoder part? Do I get your?
Yeah, I asked if the graph encoder part is trained once and then it is also frozen, or if it is query specific and it must be like trained for each query.
It is for inference it is used as frozen, but if you change, let's say we have tested on 3 different type of data sets, and for each of the data set we need to change separate GNN graph encoders. So do you mean do you asking if we need separate GNNs for different type of
No, I guess you answered the question that it will be frozen eventually. So you train the graph encoder on some data set essentially, and then you just reuse it.
Yeah.
Okay. And yeah, the second question is well, it's also a basic one, but the subgraph that you input into the graph encoder, it is initialized by the vector embeddings from the LLM for each node and each edge. Okay. And last question, the edges, they are encoded as relation types or concrete edges in the graph?
Each type, it is not each type, it is the text, each attribute on each.
So each edge. Okay, thank you.